So yes, it'll be interesting to see out of the 600 registrations, how many people
are in listen-only mode.
Good afternoon, everybody, and welcome along to DBA Fundamentals Down Under for this lunchtime session in the Australian time zone. For those of you who don't know me, my name is Warwick Rudd, and I'm your host for this virtual chapter session today. We've got a good number of attendees for today's session. A great topic by Paul S. Randall from SQL Skills on index fragmentation, internals, analysis, and solutions. I'll hand over to Paul shortly, but first, a big thank you and a call out to our sponsors, SQL Sentry, who once again this month have put up a professional edition copy of Plan Explorer, so one lucky attendee from either this session or the remaining couple of sessions left in December will receive the third and final copy. Now, another announcement is because of our sponsorship. For this month, there will be a lucky attendee will win $300, and that will be from the attendees from all of the sessions in the Australian and American time zones, and there will be a second prize draw in March for that as well. So hopefully one of you may pick up a $300 gift voucher for Christmas. Just to call out about some upcoming SQL Saturday events here in Australia and New Zealand. If you haven't registered for any of these events, they are open, and it is a great way for you to meet some like-minded professionals and learn from some great local and international speakers. And last of all, kicking off our 2016 sessions, we've got the Top 10 Clustering Do's and Don'ts by Alan Hurt. This session is also available for registration, so I look forward to seeing you all next year for the kickoff of DBA Fundamentals Down Under. So with that, I'll hand over to Paul, and we'll get the session rolling.
Perfect. Can you see everything?
I can.
Okay, thanks, Warwick. So thank you for inviting me to come and speak at your new expanded DBA Fundamentals VC. I hope it's going to go really well. Now, a couple of housekeeping things. I already told Warwick that after I'm done, I will send him a PDF of the slides and a zip file of the demos that I do. So you're going to get all the material that I'm going to present here today. And the other thing we'll do is, for questions, every 5-10 minutes or so, I'll stop and ask if there's any questions, and Warwick's going to monitor the chat screen. And if you have any questions, ask them, and Warwick will do a few every time I say any questions. And then at the end, I'll hang around for a Q&A for as long as there are questions or we're able to carry on with this. And it is being recorded as well. So, index fragmentation. A few kind of housekeeping things first of all. SQL Skills, I obviously work for SQL Skills and own it with my wife Kimberly Tripp, a bunch of other people that you can see there work for us. We do training, consulting, blah, 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 blah. Oh, we have a newsletter every 2 weeks down at the bottom there if you're interested. I do an editorial on something interesting to do with SQL Server, a book review, and we put out a little demo video. Just some completely free stuff, no advertising, marketing, or any of that kind of stuff. We do training around the world. We were in Australia actually, was it twice this year? No, just once this year, earlier on this year. We're not coming back to Australia next year, but hopefully in 2017 we'll be back. But we do have training classes all over the place. So there's an example of some of the training we do. So very quickly getting through all the marketing stuff. So here's me. I used to work for the SQL Server team for about 9 years or so. I wrote a whole bunch of the storage engine code, including the DBCC index defrag and DBCC show config, which are very much all to do with fragmentation, which is why I talk about fragmentation quite a bit. Some interesting stuff on that slide, apart from what I used to do. My email address, paul@sqlskills.com. If you have any questions about anything that I'm talking about today, feel free to send me an email about it. Just say, I saw you on the DBA Fundamentals VC, and I've got a question in your subject line, because I get lots of emails every day, and I want to make sure your questions bubble up to the top. Our blogs, all of us at SQL Skills blog an awful lot. There's tons and tons of stuff on my blog, and also I'm on Twitter as well, at Paul Randall. Now there's a very, very vibrant SQL Server community on Twitter, and it is worldwide. I will say that there are more people in the US that seem to be on it than are in other places, but there are a lot of people in Australia and New Zealand that are also on there as well, lots of MVPs and consultants and so on. So if you have a question, and you can tweet it in 1 or 2 tweets, add the #SQLHelp hashtag on the end, and you'll get somebody that will give you some help for free, which is pretty cool. And then talking about for free, one of the things I do for all of the user groups that I present at, either in person or remotely, is I'll give everybody who's never seen Pluralsight, which is an online training company that we have a lot of training in, a completely free code. You don't have to give a credit card or anything at all, just for 30 days of access to, actually now it's 140 hours of online content. Okay, so if you're interested in that, just shoot me an email and I'll send you back a free code. All right, on with the show. Fragmentation. No matter what you have been told, there's all kinds of incorrect stuff out there on the internet about fragmentation. No matter what you've been told about fragmentation, you cannot escape index fragmentation. Because as soon as you have more than one index, you're going to have an index that doesn't match your insert pattern. Okay, so you've probably got your clustered index set up potentially to match your insert pattern. And as soon as you have non-clustered indexes, by definition, they're on different keys. And so those are not going to match your insert pattern. So you're going to start to see fragmentation. And one of the other things that I see people incorrectly saying on the internet is, oh, fragmentation isn't a big issue. Right? Fragmentation itself and the fact that you've got fragmentation isn't the only problem. What you have to also think about is what causes fragmentation, because that in itself is a performance problem when it happens. So what we're going to cover in this session, about an hour or so, plus questions, is some simple ways that the storage engine uses an index B tree, and then the definition of a couple of different kinds of fragmentation. How does fragmentation happen, which is basically an operation called a page split, and then we'll look at how you can detect fragmentation, how you can mitigate fragmentation using a thing called a fill factor, and how you can remove fragmentation. And I've got a couple of simple demos that I'll do as we go along. So first off, this is an index structure. And an index has a very simple structure, and this is the same structure whether it's a clustered index or a non-clustered index. It doesn't matter in terms of fragmentation whether we're talking about clustered versus non-clustered. The structure is the same for an index, and the problems that you have around index fragmentation are the same. The only difference, of course, between a clustered index and a non-clustered index is that at the leaf level, the very bottom level there of the screen, the pages that comprise the leaf level are data pages holding data records, because the clustered index is your table. Whereas if it's a non-clustered index, they are index pages holding much smaller index records. But you can see that at each of the levels in the B tree, the black arrows there pointing left and right show that the pages at the leaf level are linked together in a doubly linked list. And this means that, for instance, this page here has in its page header a note of what this page is. Okay, these are called page IDs, so that the storage engine can navigate from page to page to page in ascending or descending order. And this is necessary because there is absolutely no guarantee that this page here, which holds the next set of key values after this one, is physically next to this page. It can be anywhere in the file group, okay, that this index resides on. You can also see that there are these red arrows pointing downwards, and the red arrows allow the storage engine to navigate through a B tree. So basically a page at one level has a link to all of its child pages. And this is how an index is structured. So the very first way of SQL Server using an index structure is what's called a singleton lookup, looking up a single record. Every access to the B tree starts at the root page. So this kind of cloud here is the metadata, which has the page ID of the root page of the index. SQL Server figures out which way to navigate through the B tree to get to the record that it wants. So in this case, it's decided to go left, and then it decides to go down here. And it finds the matching record based on the search predicate that you've said. Now, there's going to be a number of records on the pages at each level, and the way that SQL Server finds which record it's interested in is not by a brute force read every record on the page until it comes to the one it wants. It does a thing called a binary search, which is a very simple computer science algorithm for efficient searching of an ordered list of things. Okay, it basically cuts down the number of records that have to be read from potentially maybe half the records on the page or more to a small number, 4, 5, 6, something like that. It's very, very efficient. The second way of an index being used is what's called a range scan. So this is where you've given a starting and ending predicate, and SQL Server is trying to find what those records are that match. Now, you might have not given an ending predicate specifically, but if you say where say x is greater than 10, you've implicitly given an ending predicate of positive infinity. Okay. So again, every access to the B tree starts at the root page. So it comes up here, it navigates down through the B tree to find the first matching record. This is the storage engine that's doing this, specifically the access methods. The access methods gives the record back to the query processor. And the query processor does its thing and then says to the access methods, get me the next record. Now, the access methods does not have to navigate down through the B tree each time. What it does is it keeps what's called a cookie on this page, basically saying, as long as nobody changes this page, I know that the next record on the page must be the next one that might match the search predicate. And so it can just carry on looking at the next record. If, while the query processor was processing the first record that was given back, somebody changed this page, then the storage engine cannot 100% know that the next record is the right one. So it then has to go back and revalidate its position. But let's just say, for argument's sake, that the pages don't change. So the access methods gives the next record back, and so on and so on and so on, until it gives back the last record on the page. Then the query processor says, hey, get me the next record. The access method says, oh, no more records on the page. So it goes up to the page header, and it uses the pointer, remember I told you about the doubly linked list, and says to the buffer pool, please read me this page into memory. If this page is not already in memory, then the buffer pool has to go and do a physical I/O, and our scan has to wait. Eventually, the page is going to be brought into memory, and our scan continues, giving back all of these records, reading the next page, giving back all of these records, reading the next page, giving back all these records, until it comes across a record that doesn't match the search predicates anymore, and it says no more records. So that's a range scan. Okay, so you've got two simple ways of SQL Server making use of an index structure, either looking for a single record or doing a range scan. There are other uses of an index structure, but they're not pertinent to our discussion of fragmentation, so I'm not going to cover them here in this short session. Now, I didn't quite tell you the whole story about read ahead. Okay? So remember when, on the previous slide, the access methods got down to here and asked the buffer pool, please read this page into memory. What would be really cool for scan performance is if this page is always in memory. Okay? And the way that SQL Server does that is, if it's doing a scan, what it's going to do is make sure that these pages ahead of the scan point, up to 1,000 pages ahead of the scan point, are in the buffer pool. So it pre-reads them into memory. And that mechanism of pre-reading the pages into memory is called reading the pages ahead of the scan point, or for short, read ahead. So the way the read ahead works is it uses the doubly linked list at this level. Because at this level, if you think about it, what these pages have here, these 3 pages, is a list of all these pages in key order, because that's how an index structure works. Okay? So by using the list of page IDs at this level, the storage engine can pre-read the pages down here, making sure that it's reading the correct pages in key order, so that when our scan needs them, they're already there. And it goes faster. The scan's going to be more efficient because it's not going to have to wait. Now, the read ahead works on varying sizes of IOs. It can ask for instance, 1 page to be read in, 8 pages to be read in, 32 pages, and so on. It's obviously much more efficient for read ahead to do larger IOs. Consider reading 8 pages in. Is it more efficient to do a single physical I/O that goes down the I/O stack once, reads 64K, which is 8K pages, and then returns? Or is it more efficient to do 8 trips down and up the I/O stack, each reading 8K? Obviously, it's the former. So read ahead is more efficient when it can do larger I/Os. The problem is the I/O size is determined by whether the pages it's reading are in physical order. Okay, so it knows they're in logical order, but if they're not in physical order as well, then it can't do as large IOs, and it has to do smaller IOs. Right? And this is getting towards the definition of fragmentation here. So this slide basically has everything that I said on the previous slide, okay, apart from this bit here. Okay? There is a feedback mechanism to make sure that the read ahead doesn't go tearing ahead too far of where the scan point is. Okay? So I said that when there are pages that are not in the same physical and logical order, that's when we have problems. So if, for instance, consider maybe there's like 1,000 pages here. Okay? If it's building up a large I/O and it comes across a page that's the next logical page, that is not in physical order, then it has to do smaller IOs. And that, when the page is not in the right order physically, is called fragmentation. That's the basic definition of fragmentation. So Warwick, any questions on the slides that I've covered so far?
No, Paul. Well, all good.
All right, Karen. So we did this slide. So fragmentation, logical fragmentation. The basic definition of logical fragmentation is when the next logical page at the leaf level of an index is not the next physically contiguous page. Okay, that's called, the next page is called logically fragmented. Now there are other names for fragmentation. Right, for instance, external fragmentation and internal fragmentation. I do not like these other names. I find them confusing. I like to use what's in books online because, to be honest, I wrote books online for this stuff. So logical fragmentation is what I'm going to call it. It used to be called logical scan fragmentation in earlier versions. So in its simplest form, logical fragmentation prevents optimal read-ahead. And if you're preventing optimal read-ahead, that means you're potentially slowing down the performance of your scans. It doesn't guarantee that it's going to make it worse. In other words, just because you've got logical fragmentation doesn't mean you're going to have a performance issue, right, because of the logical fragmentation, right, but it can do. Now it says there that it doesn't affect pages that are already in cache. And basically, if you have a small index, it's probably going to already be there in memory, but even if it's not, a small index isn't going to take very long to read into memory, and so a scan of it's not going to be very big, and so you're probably not going to notice the performance effect of having logical fragmentation on a small index. So some of the definitions and guidance that I had to come up with were back when I was at Microsoft. You might have seen guidance saying, if your index is less than 1,000 pages, don't worry about fragmentation. Okay, that was guidance that I came up with when I was at Microsoft because people needed to have some guidance from Microsoft about when they wanted to care, when they should start to care. And that came from a lot of the times when I was on the old Usenet news groups and forums, and people would say things like, oh my goodness, I've just rebuilt my index and I've still got 45% fragmentation. What do I do? And I'd reply back from my office in Microsoft saying, how many pages does your index have? And they come back and say, 12. And I'm like, dude, it doesn't matter. Okay, just don't worry about fragmentation with a small index like that. So that's where that guidance of like 1,000 pages or less, and I've put 1,000 to 5,000 pages there because as hardware's got an awful lot faster, you might not even notice the difference for an index up to a few thousand pages. So that's logical fragmentation. That's the kind of fragmentation that most people think about. The other kind of fragmentation, the one that most people don't think about, is low page density. Okay, and again, there are these alternative names which I don't like, but I'm just making sure that you know what they are. Excuse me a second. So page density is where the fullness of the page is not optimal. In other words, there's a bunch of empty space on the page. So the problems that you can have from having a bunch of empty space on the page is obviously the data density of the data on the page is low. So the more wasted space there is, the more pages you're going to have to store the same number of records, which means that your disk space you're using is more. Which also means if you have more pages, then you're having to do more IOs to read that same amount of data, obviously. And when a page is in memory, it's taking up 8K of the buffer pool, even if it's only got, say, 100 bytes of space used on it. So having low page density can mean that you've also got a bunch of wasted space in the buffer pool, which is not good. Now here's the results of a survey that I did a few years ago now, and I got information back from just random people like yourselves across the world. And what I did was I put some code out there that would analyze the buffer pool and say how much free space there was. And do I have the animations? No, I don't have the animations here. But if we look, so what is this showing us? Look at here. So if we've got a 30%, I would say anything below 30% is acceptable because of people using index fill factors. And we'll talk about index fill factors a bit later on. But that's where you are deliberately causing wasted space on your pages. You're basically trading off one performance issue for the potential for another one, and I'll talk about that a little bit later. But let's look at some outliers here. So what we've got here, this is a logarithmic scale on the x-axis of the amount of memory that's actually in use holding data file pages in memory. Not the size of your buffer pool, but how much is actually in use. So on a logarithmic scale, this is probably around 200 gigabytes. And let's go and look at this guy here. So this here, if we go back over to our y-axis. On the y-axis we have how much of all that space that's in use is actually empty space. So it's making use of the fact that there's a DMV called sys.dmos buffer descriptors that will track in real time how much free space there is on every page that's in the buffer pool. And my code just basically goes and aggregates it all. So this system here, 200 gig of buffer pool space with 60% of it is empty space. That's an incredibly bad use of the memory that's on that server. Right? So let's have a look at some of these here. So here we've got even say, well, let's look at these guys. So this we've got like 10 gig of buffer pool space in use, and it's 90% empty. So that's a horrible amount of free space for such a small buffer pool. This system here, and probably this system here, are going to be suffering from a very large amount of page reads happening all the time, or physical page reads. Depending on what the workload is, of course, it could be that the entire workload's memory resident. But if the workload's not memory resident, then there's going to be lots of page reads happening, and that's going to be slowing things down. So if you don't take away anything else from this session, go to that blog post there and run the code and see what your server looks like in terms of how much free space is there in the memory that's being used to store data file pages. And if it's anything more than like 30% or so, you've got a big fragmentation problem that you didn't know about. And that could be causing you a big perf issue. I'm not going to say it will be, because there's no absolutes in SQL Server apart from should I always have any kind of regular shrink running. The answer is always no. Everything else, the answer starts with it depends. So you might have a perf issue if you see you've got a large amount of empty space here. Okay. How are we doing for questions? Anything yet?
Okay, so Paul, Ashish is asking, how do indexes work for in-memory tables? Are these indexes also get loaded in memory too?
That is a question that is way beyond the scope of what we're talking about here. So what I can do is the person that asked me that question, if you want to send me an email with that question in, I will provide you the answer. But given we have got such a small amount of time, I don't want to get into how all that stuff works because it's not really pertinent to how fragmentation is happening.
Okay. One other question, how does fill factor affect page density?
We will get to fill factor in a few more slides, so hold that question and it will become clear. I will answer that as I talk about it.
Okay, and then the last question, this relates to your current slide. Is it safe to run this code in production?
Absolutely, 100% safe. All the code on my blog, unless I specifically say in red letters, beware, is safe to run in production. But this is especially safe. Now, what it's going to do is if you've got a very large buffer pool, it might take like an hour or so to come back. But it's not going to be causing any performance issue at all. It's just that there's a very large number of pages in memory that it has to get the data back from. But it's not going to cause you any performance issues at all running this code.
All right, very good.
Is that all?
Yes.
All right, perfect, thank you. So what causes fragmentation? Fragmentation is caused by an operation, generally caused by an operation called a page split. And a page split is where an operation has to happen on a certain page that needs some space. For instance, you go to insert a record into a table, and the table has a clustered index. The insertion point of your new record in the clustered index is determined by exactly one thing. What is the key value? Okay? There is absolutely no choice of where the new record has to go. Okay? If the page that's identified as where this new record has to go does not have enough space, new space must be created, and it's done by a thing called a page split. Let's say that you have a record on a page that you do an update on. Right? If the update is on a record in an index, the index record has to stay in the position that it's in the index. So if there's not enough space for the updated record, there has to be space created on the page, and so the page has to undergo a page split. Another thing that can cause an index record to increase in size is if you turn on snapshot isolation, which makes use of the versioning mechanism. And snapshot isolation, either actual snapshot isolation or read committed snapshot isolation, uses a mechanism called versioning. And Long story short, when versioning is in play, the updated record gets a 14-byte tag added onto the end to support the versioning mechanism. And that is the same as updating the record, essentially, and making it 14 bytes longer. So one of the side effects of using snapshot isolation can actually be index fragmentation starts to happen. Because if there's no space for these records to expand by 14 bytes, page splits are going to have to occur. Now, there's actually one more insidious thing that isn't talked about very much, which is in availability groups. If you use readable secondaries, as soon as you create a readable secondary, every access to that readable secondary is converted under the covers to use the snapshot isolation level, which means it has to make use of the versioning mechanism, which means there has to be 14 bytes of space for all the records that change on the readable secondary. The only way for that to happen is for the 14 bytes of space to be created on the primary replica, because the two databases, essentially the primary replica and the secondary replica, have to be essentially byte for byte copies of each other, apart from things that aren't used between the two databases, like snapshot isolation. So as soon as you create a readable secondary, the primary starts to create 14-byte tags to allow the versioning system to work on the readable secondary. And if that means that there's no space on the pages on the primary replica, then you're going to start to see page splits occurring, which are going to start to cause fragmentation on your primary replica. So be very aware if you're using readable secondaries that you might have to take account of the potential for fragmentation to start to happen on records and indexes on your primary replica. And you can work around that, and we're about to talk about it using a thing called fill factors. So when a page splits, basically what it's going to do is create a new page and move a bunch of records to the new page. And it tries to do it usually at around 50-50. So it's going to move around half the records to the new page. So what happens is, let's say we're doing an update into page B here, and page B is completely full. So what the storage engine has to do is split page B. So it creates a new page, and we've called it down here page B1. And page B1, because it's essentially the second half of the records of page B, is going to basically fit into the space between B and C. Because B was holding all these records, let's say from 10 to 20, and C had 21 to 30. And now what we're doing is taking 15 to 20 and putting them on a new page. So the page has to go logically in between these two to preserve the way that an index works with the key ordering. So page B1 gets inserted essentially into the leaf level of the index between pages B and C. Half the records get copied from page B into page B1. The page header of B points at B1 now instead of C. The page header of C has to change to point back to page B1 because it no longer points at B. And then also to link the page into the B tree correctly, there has to be a new pointer coming from page P here, navigating down the B tree, pointing at page B1. Right. So page P might also be full, in which case when it goes to insert the new row, that page might split. And so you might see a split that kind of cascades all the way up to the root page of an index if it's a multi-level index. Okay, it doesn't happen very often, but it can happen. So that's how a page split works, basically. Create a new page, copy the rows over, fix up the various page headers. Every single thing that it does as part of the page split is fully logged. It's done by a thing called a system transaction, which commits and can't be rolled back. So if you did begin tran, update a record on page B, it caused a page split, and you did rollback, the page split would stay there. Page splits generate a lot of transaction log. They're fully logged no matter which recovery model you're in. And so this is the thing that many people don't think about, is this is what causes fragmentation. So the cause of fragmentation, which is page splits, generates a bunch of extra transaction log, which has to be backed up and restored and sent to your mirror and sent to your AG and scanned by replication and so on and so on and so on. So you've already had a performance issue by the time you notice you've got fragmentation. So what you want to try and do is avoid the fragmentation happening in the first place. In other words, avoid page splits from happening in the first place. This is one of the things that is really a hot button of mine, where people say, well, if you have SSDs, you don't care about fragmentation anymore. Yes, you do, because SSDs don't stop page splits happening. They don't stop all that extra transaction log from being generated. You cannot avoid fragmentation. Okay, it's going to happen to you. And having faster hardware isn't going to make things any better. You have to know that fragmentation exists and take steps to mitigate and avoid it if you can. So, tracking page splits. Okay, and I've got a demo. Oh, good, I've got a demo coming up. So, tracking page splits, and we'll do a demo. Unfortunately, there are two kinds of page splits. Okay, the ones I've been telling you about I call nasty page splits. There's also another kind of thing, which is if you have an append-only insert pattern where maybe you've got an identity value key, for instance. So every record you insert is always going to be on the right-hand side of your B tree, conceptually. Then you're inserting records, it fills up the page, it allocates another page. It fills up the page, it allocates another page, and so on and so on. Unfortunately, the access methods calls the allocate another page, in that case, a page split. And the two kinds of page splits are lumped together in all of the methods of tracking page splits. So the access methods performance object page splits per second counter tracks both of them. The leaf count column, I think it's called, in the DMDB index operational stats DMV counts both of them. The extended event for page splits counts both of them. Okay? They tried to extend it in 2012 to make it a little bit easier to tell, but there are still cases where a good page split will cause the page split extended event to fire. So basically the only way that you can always tell that a page split is happening, sorry, a nasty page split is happening, is by looking in the transaction log. And you can do that in two ways. In 2012, there was a new extended event that was added called transaction log. And there is a specific log record that is only generated when a nasty page split occurs. It's called LOP delete split, and I talk about it in that blog post link there. And if you're not on 2012, you don't want to use extended events, I've also got code in that blog post that will allow you to scan the transaction log itself, or even a transaction log backup using undocumented table value functions, fndblog or fndumpdblog, to look to see page splits happening. So it's very hard to track page splits actually happening in real time, but you can do it if you want to. Any questions? Work.
Okay, so Paul, we've got a couple of questions. First question, there appears to be a lot of page splits in SharePoint databases. What are the best fill factor for these databases?
Okay, so yes, so SharePoint, unfortunately, and many other products use a GUID as their cluster key. And that's one of the best random keys for causing fragmentation, because you have an insert happening at a random point in your index, and so the odds are it might have to do a page split to create some space for the new row. So when we get to fill factor, what I'm going to talk about is a general mechanism for determining what a good fill factor could be. And it's no different on SharePoint or any other database, to be honest. Now, there is a SharePoint maintenance white paper that specifies setting 80% as an instance-wide fill factor. I generally shy away from setting an instance-wide fill factor, and I'll explain why when we get to fill factors. But something like 70 or 80, if you absolutely want to set one and just walk away, 70 or 80 could be a good one to go with. Okay.
Next question, what is the difference between page split and torn page?
Oh, they're totally different. So a page split is where a page is having to make space to allow an operation to occur. A torn page is where a page is being written out by the buffer pool and the power fails, and not all of the 16 512 byte chunks of the page make it to the disk. And so what you've got is you've got some disk sectors of the old version of the page and some disk sectors of the new portion of the page. Nothing to do with fragmentation at all. This is to do with corruption, and SQL Server can detect that.
Okay, so on an index page, are records stored in sorted order without leaving any extra space? If yes, if any intermediate value comes up, does it get stored in sorted physical order, or is that page logically linked appropriately?
Okay, so the answer is no. Records do not have to be stored in the key order that is defined. Now, when you first create a brand new index or you rebuild an index, then yes, the records on the pages are going to be ordered in the same physical way as the key is ordered. However, the storage engine can make use of whatever space on a page that it wants. So what it could do is, and I'm going to draw freehand here, which is always a bad thing because I'm a terrible, terrible artist. So if this is a page, and usually when I'm teaching I've got a digital whiteboard, but I'm just using my mouse here. So let's say we have this is the page header, and we have 3 records on the page. We have this one here with the key value 1, we have this one here with the key value 3, and we have this one here with the key value 2. And we have a numeric key. Now clearly these records are not stored in the right physical order compared to the key order. The way that all this works is there's a thing down here at the bottom of the page called the slot array. And the slot array is a kind of indirection mechanism where it grows backwards from the end of the page, where the key value that is the lowest on the page for an ascending key index is pointed to by the very first entry in that slot array. And the next one is pointed to by this one. And the next one is pointed to by this one. Okay. So let's say that somebody deleted the key value 1 and that record got deleted. Okay. So the record wouldn't be there anymore. And then somebody came a little bit later on and inserted key value 4. So if there's space on the page for key value 4, then the record will be inserted and it will reuse some of that space and it will be 4. And there'll be an entry pointing to it like this, because this one will have gone away. Right. It doesn't matter that the records are stored in what seems to be the wrong order, because the slot array down here always allows the records to be accessed in the correct order. In fact, the only way to access the records on a page is via the slot array. And so the storage engine will always see them in the correct order, but they don't have to be physically stored in the correct order. And that's a very good space efficiency and performance efficiency mechanism. I'm done.
Okay, I have got some more questions, but what we might do is we might skip into the demo, and I'll bring these up towards the end of the session in the Q&A.
Yep, absolutely. Okay. All right, so let's get into the demo. So I've just got some simple demos. The first one I want to do is I want to show you how expensive page splits can be in terms of the extra logging that happens. So I'm going to create this little database called page split test. And then I'm going to create a table that has roughly 1,000 byte rows, and I've got this forcing value here that's going to force it to be roughly 1,000 byte rows, and then a clustered index. And then what I'm going to do is I'm going to create a scenario where there's enough space on the page in my clustered index to insert 1 extra record, but not to insert 2 records. The second one's going to cause a page split. So I go ahead and do that, and then I'm going to look to see how much transaction log is generated by an insert that doesn't cause a page split. So I begin a transaction and do an insert. Then I'm going to use this DMV, sys.dmtran database transactions, scoped down to my database to see basically how much transaction log was generated by that insert. 1,256 bytes. Now, depending on which version of SQL Server you are on, the further back in time you go and the earlier your version is, the lower these numbers are going to be by a few bytes, because log records basically change in size. They increase in size every version. So 1,256 bytes, and then compare that with the one that does a page split. 7,580 bytes. So what's that, about 6 times more transaction log for a 1,000 byte record, okay, when you have to do a page split, which is kind of sucky. So let's drop it down now to roughly 100 byte records. So I drop my big rows table and I create a medium rows table. And the same thing, I'll create a situation where there's enough space for 1 but not enough space for 2. And then an insert without a page split, 356 bytes. And then with a page split, 356 bytes versus 6,772 bytes, which is what, 18, 19, 20 times, something like that, 18 times, 19 times more. Okay, so as the size of the record gets smaller, the extra cost in terms of percentage of having to do the page split increases. So let's drop it down to roughly 10 byte rows. Well, that's probably more like 18 bytes, something like that. And then I'm going to create a situation where it doesn't do a 50-50 page split. It's going to do what's called a skewed page split, where it determines that it's better to split at the boundary between two sets of values. So in this case, an insert without a page split, 268 bytes, compared to with a page split, 11,172 bytes, which is what, 46 times more transaction log, which is a huge amount of extra transaction log to think about if, and that's the end of the demo, if you've got lots and lots of page splits happening, you're generating all this extra transaction log which you can avoid. And as I said, it's all having to be backed up and restored and sent across your HA features and blah, 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 blah. It's bad news. So you don't want page splits to be happening if you can avoid it. So that's the end of that first part of the demo. Okay. So back over to the slides. How are we doing for time? 10 past. Okay. So what causes fragmentation? What causes fragmentation is anything that causes a page split. For instance, having a random key. Okay, so the insert does not match the way that an index works. So anytime you have a random key value that has to be inserted randomly somewhere in the leaf level, you have the potential for a page split to occur. And one of the most common and easily chosen random keys is a random GUID generated by the new ID function in SQL Server or generated in your .NET layer, for instance. And a GUID cluster key, a random GUID cluster key, can even cause fragmentation issues in non-clustered indexes as well, as I'm going to show you in the next part of the demos that I'm going to do. So any kind of random key, any non-clustered index key is, unless it's exactly the same as your clustered index, is going to cause fragmentation as well. So this is why I said as soon as you have non-clustered indexes, you can't avoid fragmentation. Any updates to variable length columns, okay, in a table where there is no space on a particular page. The record has to get longer, there's no space, it has to cause a page split. Using snapshot isolation can do that. Using a readable secondary can do that, for instance. Not having a fill factor configured when you have one of these situations can also lead to page splits occurring. So what you want to try and do is, if you can, change the keys so it doesn't cause fragmentation. That's very much easier said than done. You can't do it for your non-clustered indexes. And for your clustered index, it might be very hard to make a schema change like that. So the thing you're going to have to do is use fill factors. Right? Another thing that can cause fragmentation, if you consider page density as a kind of fragmentation, is having a very wide schema. For instance, if all of your table records are basically 5,000 bytes, you can only fit one of those on every page. So you're wasting 3,000 bytes on each of those pages, and that can cause a performance issue by having too much space being taken up by nothing. Right? And even deletes, as it says there, can cause fragmentation. Because if you think about it, if you have an append-only insert pattern, and you ever go back and delete earlier records, the new records that are being inserted are always going to be inserted at the right-hand side of your B tree. So they're never going to go back and reuse the space that was freed up by the deleted records. And so if you've got lots of deletes happening, you can have a very slowly increasing page density problem, or I should say a decreasing page density problem. Okay, that you might have to go and periodically address. And that's not a thing you address with a fill factor. That's a thing you address by rebuilding or reorganizing your index. So fill factor. What a fill factor does is it says to the storage engine when the index is being created or rebuilt or reorganized, leave space to allow things like row inserts or updates to happen. Okay, so leave free space. In other words, I deliberately want to leave free space and lower my page density to allow there to be space for these operations that cause page splits so that a page split doesn't happen. So you set a fill factor, and then periodically you have to rebuild or reorganize your indexes so that that amount of space is put back again. And the idea is that you pick a fill factor and the periodicity that you do your index maintenance such that pages in that index don't split. They fill up and fill up and fill up, and they're just about to get to the point where they split, and then you rebuild them or reorganize them again, which puts back the amount of free space. So there is an SP configure option, which is the fill factor for all the indexes that's going to be used. I do not recommend that you set that. I recommend that you leave that alone. It's going to be set to 100, which is basically the same as 0. In other words, don't leave any space. And what I recommend you do is for only those indexes where having or removing fragmentation causes you or fixes a performance problem, set the fill factor just for those indexes. Okay? And that is easier than setting a fill factor for the entire instance and then having to go and find those indexes where you don't want there to be a fill factor set and specifically set them to be 100. Okay? So do it the smart way and only set fill factor for those indexes that you care about. Okay? There is a thing you can do where you can take the fill factor that you've set and push it up into the upper levels of the B tree as well, because fill factor is just for the leaf level. And it's called pad index. I very rarely see this being used, but if you are having performance issues because of fragmentation in the non-leaf level of your index, you can address that as well. Right. Now, for an unchanging set of data, like in a data warehouse, for instance, or if you have an append-only insert pattern where you're not doing any updates, you're not using versioning, you don't have a readable secondary, then you don't need to have any fill factor set because you don't have the possibility of page splits occurring. But if you have an OLTP system where you've got random keys happening, or maybe you're having to make use of versioning to address locking issues, or you're using readable secondaries, then you might have to have a fill factor, because that's the only way that you can mitigate page splits occurring, is to leave free space for them. So for an OLTP system, what value do you use? And the magic answer is, there isn't a magic answer, unfortunately. If there was an answer, I would tell you what the answer would be. But there is a method you can use, which is, for those indexes that you care about, you pick a fill factor, a starting fill factor, you put that in production, you monitor the fragmentation, and then after a week or so and you see whether the fragmentation's really heavy still, you might consider increasing your fill factor. Okay? And the fill factor you set, for instance, if you set a fill factor of 90, that means leave 10% free space. Okay? Don't get it confused and do it the other way around, or your indexes will get very big very quickly. So you pick a fill factor, put it in production, monitor, and then maybe tweak the fill factor, or tweak how often you do the index rebuilds or reorganizes. And a very common first guess is 70 for those indexes you care about. In other words, leave 30% free space when the index is rebuilt or reorganized. Okay? And it doesn't really matter what your application is, whether it's SharePoint or anything else. Okay? Follow that methodology. Pick a number, put it in production, monitor, tweak. Okay? So how do you monitor? The way that you're going to monitor, the easiest way to monitor is you're going to use this DMV, DMDB index physical stats. Okay, and under the covers, this is what things like SQL Sentry's Performance Advisor is doing. It's using this DMV to figure out what kind of fragmentation you have when you have the fragmentation module. The DMV is pretty cool, and it's also dangerous at the same time because it's not a true DMV. Okay, DMV is a kind of catch-all phrase to mean all of the dynamic management objects. And DMV specifically stands for Dynamic Management View. However, this is not a view. It's actually a DMF, a Dynamic Management Function, and it's the most expensive function because the fragmentation level of your index is not stored anywhere. When you run the DMV, it has to go out and calculate all of the fragmentation information. So depending on how you run it, if you say, I want the detailed mode and do it for every database on my server, it's going to have to read basically every page on your server to try and figure out all the fragmentation for all the indexes and all the databases. So generally don't do that. Okay. There's a number of different ways you can do it. There's limited, sampled, and detailed. Limited is the default, and that doesn't read the leaf level. Do I have the slide here? Yes, I do. Okay. I trimmed a few of the slides out this morning because I was making it fit in the hour that we've got, and I couldn't remember which slides I trimmed out. So this is how the limited mode of the DMV works. It basically uses the same trick that read-ahead does, because if you think about it, all the pages down here, their page IDs are stored up here in logical order. So if the logical order of these page IDs matches the physical order, there's no fragmentation. If they differ, we can work out what the fragmentation is. So the logical fragmentation can be worked out just from reading this list level. And that is hugely cheaper than having to read the leaf level in its entirety as well. But if you use the limited mode, the only thing that you get is fragmentation and how many pages there are. You don't get to know the page density because you can only get that from reading the leaf level itself. The detailed mode does a limited mode scan first, and then it reads all of the leaf level. The sampled mode does a limited mode scan, and then instead of reading all of the leaf level, it just reads every 100th page. If your index has more than 10,000 pages, it'll just read every 100th page. And so it gives you a kind of estimation of things like the page density. There's all kinds of things that are output in the DMV, and the things that you really need to look at are the logical fragmentation, the page density, and how many pages there are. When I designed the DMV to replace DBCC ShowConfig, we figured out that there were all these different things that DBCC ShowConfig used to show you, and it was confusing. So we thought, let's be smart and get rid of a whole bunch of them and invent a new way of describing fragmentation. And you'll see this described in books online, and we called it fragments and average fragment size. And I think we failed miserably because it's just as complicated to understand as anything else. So the easiest way to think about it is logical fragmentation and number of pages. That's what most people use, just those two things. And then also you can add in page density as well if you're interested in that. So how are we doing? Any quick questions?
A couple of quick questions, Paul. So variable length columns, can those cause page splits when wider values are updated in the records at the later point in time?
Absolutely, because if let's say you've got a varchar 100 and you store the value Paul, it takes up 4 bytes, okay, plus all the extra metadata overhead. If you then update it to store Paul Randall, then you're taking an extra 6 bytes. If there aren't 6 bytes of free space on the page, it's going to cause a page split. So yes, absolutely, that is one of the causes of page splits.
The next one is there another way to measure fragmentation without using the DMV?
Is there another way to measure fragmentation without using the DMV? All the methods of measuring fragmentation use the DMV under the covers. So the Management Studio wizard that does it, the fragmentation wizard, I can't remember exactly what it's called, it uses the DMV under the covers. No, there's no other way of doing it basically, because it has to do the analysis. Well, I guess you could write your own method of doing it, but in SQL Server there's no other way of doing it apart from using the DMV, because it has to do the analysis of the page IDs in the pages. Now you could, if you wanted to, you could write your own code that uses DBCC page to do exactly what the DMV is doing, but I wouldn't bother. I'd just use the DMV if I were you.
Okay, this one's probably not going to be a quick one, but how SQL Server will identify which page got modified and which page did not?
I'm guessing the person is saying when a page split occurs, which page gets modified. The way that you would do that is you'd have to look in the transaction log. That would be the only way you could tell, is to look in the transaction log. Well, let me see. Yes, it's the only way you could tell, because I was going to say you could look in the buffer pool and you could see the pages are marked dirty, which means they've changed, but the page that's splitting and the page that was created are both always going to be marked dirty because they've both changed. So you can't tell in any way apart from the transaction log what actually happened to those pages. So you'd have to do transaction log analysis to tell.
All right. So we'll hold on to some of the others and continue on with the session.
Perfect. So let's have another little demo. And this is a demo showing you using the DMV. Now it's hard to do a really cool, sexy demo around the DMV. It's like, look, there's fragmentation. But I'm going to try. So what I've done here is I've got this script which I've already ran because it takes about half a minute and we're pressed for time in this session. So what it does is it creates a database called GUID-test. And it then creates 2 tables with exactly the same schema apart from one thing. One's called bad key table and one's called better key table. And they're exactly the same apart from the definition of column C1. In bad key table, it's a random GUID. In better key table, it's a sequential GUID. Then there's a clustered index on C1 and a non-clustered index on C2, which is a date time. And then I go ahead and create 250,000 rows in each of them. So to look at the fragmentation, what we're going to do is we're going to use the DMV. And what I'm going to do also is show you how expensive they are in terms of the number of IOs they do using extended events. And this little bit of code here was just me going out and using XP command shell to go and run some delete code on my server. Anyway, so my extended event session is just going to look at the SQL statement completed event, and it's going to grab the SQL text so we can see the number of IOs that were done and how long it took from the SQL statement completed event. Now, I'm running on 2014, but I'm using the old syntax, and this is so that all of you that are still running on 2008 or 2008 R2 can go and run this code as well. So I go ahead and define my extended event session, and then I'm going to run the 3 types of the DMV, detailed, sampled, and limited. And then we'll stop our event session, and in a minute we'll look and see how expensive those were. So there's the 3 runs of my DMV. Now the DMV is pretty simple, okay? Object ID, index ID, and so on. And if we look for the detailed mode, this is the detailed mode, we get 1 row for each level of the index, and it gives us all the fragmentation information about each level of the index. Mostly what we're interested in is just the leaf level, index level 0. The fragmentation to like 12 decimal places, and a whole bunch of other things, page count, the average page space used in percent, this is our page density, and then a bunch of information that we get from the leaf level, none of which is pertinent to what we're talking about here. The sampled mode, you get 1 row for each index leaf level, and what it's done is it's read every 100th page and then multiplied by 100. Okay. Down at the bottom here we have the limited mode, and what the limited mode does is it gives us 1 row for each leaf level. It gives us the average fragmentation in percent, which is our logical fragmentation. It gives us the page count, and that's it, because it doesn't read the leaf level. Okay, so the output of the DMV is pretty simple, right? How expensive are they? Now, this is where there's some different code. If you're on 2012 or 2014, you run this first bit of code. If you're on anything below 2012, you run the second piece of code. Okay, because extended events are stored as XML, and the XML format changed for these. So here's this. So if we look here, the detailed mode read 40,000 pages. There's 2 tables with about 20,000 pages each. That's why it's 40,000. Detailed mode read 40,000 pages to 52 milliseconds, all the way down to the limited mode. It only read about 250 pages because it's not reading the leaf level. Remember, it's reading the level above. And it only took a couple of milliseconds. The moral of this story is if you can run the limited mode, just run the limited mode. Okay, it does a lot less work. What you could even do is take your database, restore on another server, and run the DMV over there through a linked server query, and then get the information back and do your maintenance on your prod system. Okay. But anyway, let's have a look at the fragmentation in a bit more human-readable form. So my bad key table clustered index here, 99% fragmentation, random GUID. My better key table with a sequential GUID, less than 1% fragmentation. My non-clustered index on the table that has the random GUID clustered index, almost 30% fragmentation. That's because this is a non-unique, non-clustered index, and it's on a date time column. And my laptop here can insert many, many hundreds of records every 3.3 milliseconds, which is the minimum time period that a date time column can resolve. So my non-clustered index key is all the same for hundreds and hundreds of records at a time, which means that the insertion point is determined by the next portion of the key, which in a non-unique, non-clustered index is the cluster key. And so I get my random inserts happening into my non-clustered index, causing fragmentation there as well. Okay. So we'll leave these indexes fragmented, and then we'll talk about methods of removing fragmentation. Okay, and then I'll show you getting rid of the fragmentation a little bit later on. So Warwick, I'm just going to carry on now without any more questions till we get to the end, because we're going to run 5-10 minutes over anyway, and then we'll do a long Q&A session at the end, if that's okay with you.
Yeah, that's fine, Paul.
So correcting fragmentation. Once you've determined that you've got fragmentation from running the DMV, how are you going to get rid of it? There's 2 realistic choices. You can rebuild the index or you can reorganize the index. Okay? And I'm going to compare the 2. There is another thing you can do, which is create index with drop existing equals on, which is exactly the same as an index rebuild, but you have to specify the entire create index statement. You're not going to use that just to do a rebuild. You're only going to use that if you want to change something about the index, like moving it or partitioning, unpartitioning, something like that. You could not remove fragmentation. Just because you've got fragmentation doesn't necessarily mean it's a performance issue, right? And you could, if you're like an involuntary DBA, you could just rebuild everything every day just to make sure you don't have any fragmentation. I think that's pretty much overkill, though, and you probably don't want to do that. Right? Now that you've watched this session, you want to take a more methodical approach to removing fragmentation. Right? So basically, you're going to rebuild or you're going to reorganize. So rebuild basically takes the index and builds a new one. And it's atomic, which means that when it's done, you've got a brand new unfragmented index. That's also a bad thing, because if you don't let it finish, you don't get anything. It rolls everything back. You don't have to know anything about the index at all. It's just a straight rebuild. You can change the number of CPUs it uses, because it's going to run in parallel on Enterprise Edition. You can limit the number of CPUs it uses, or you can actually increase the number of CPUs it's going to use if you've got some kind of max DOP controls. If you have any index column statistics, it's going to rebuild those with the equivalent of a full scan, which is a good thing. A reorganize doesn't. It can't do that. And it can touch a single partition. So you can do a single partition rebuild, either online or offline. Online only from 2014 onwards. What else to say there? Minimally logged. So if you're in the bulk logged or simple recovery model, then generally you're going to be using bulk logged rather than simple. It's not very often you're using simple. Then the index rebuild only logs the allocations of pages, not the actual inserts. So it generates less transaction log, which can have a good effect on the size of your transaction log. Your log backup's probably going to be about the same size, though, as if you did it in the full recovery model. But a minimally logged index rebuild can have good performance effects on your transaction log. Now, if you're doing an offline rebuild, there's a thing called a schema modification lock is required for the table, which is, you can think of that as a super exclusive lock. You can't do any reads or writes to the table for an offline index rebuild of any index. If you're doing an online index rebuild, there are some blocking locks that are held, right? And we'll talk about those. Do I have that slide in there? Let me just check whether I have that slide in there. I do. Okay. So we'll talk about the locks that are required for an online index operation in a few more slides. It's actually potentially blocking and long-term blocking, but almost online index operations wasn't a very good marketing term, so we decided to call it online index operations. A reorganize. So this is the index defrag, basically, that I wrote for SQL Server 2000. It's always online. It's never going to take a blocking lock unless you specify something like a tab lock X, or you have a query that needs to escalate to a table level exclusive lock. Right? You can stop it at any point you want, and it's not going to roll things back, which is, again, different from a rebuild, where unless you let it complete, you lose everything. It does nice progress reporting for you, which an index rebuild doesn't. It's going to take all your off-row lob data and try and squish out any extra space. It's called lob compaction, and that's on by default, which an index rebuild won't do. A rebuild won't touch your off-row lob storage at all. For a low fragmentation index, you're going to be better off doing a reorganize. For a heavy fragmentation index, you're going to be better off doing a rebuild, just because of the way the algorithms work. And probably one of the best things about it is it doesn't need any extra disk space. It just requires one 8K page. So the reason that I wrote index defrag in the first place was as an interruptible, low space required online alternative to DBCC DB reindex in SQL Server 2000. Okay. So comparison points. How much space do you have? If you're rebuilding if you've got a 1 terabyte index that you need to remove fragmentation, you're probably going to be forced to do a reorganize rather than a rebuild, because a rebuild is going to require another terabyte. How much transaction log is generated? A reorganize is always fully logged. A rebuild could be minimally logged. How much fragmentation do you have? How much do you have to be online? Right? Is there no possibility of blocking being allowed at all? That means you're going to have to do a reorganize. Are you want to be able to interrupt it or not? Do you want progress reporting or not? So these are your comparison points, and I can't tell you what the right option is for you. You're going to have to make use of what these comparison points are and choose a rebuild versus a reorganize. There's also some metrics that you can use about when to rebuild versus defrag, and you might have seen these numbers in books online or described elsewhere, which is for a very low amount of fragmentation, don't do anything. 5 to 10%, up to 30%, do a reorganize, and anything more than that, do a rebuild. These were numbers that I made up when I was at Microsoft because people wanted some guidance. Didn't quite make them up, though. I mean, I talked to customers, I talked to the customer advisory team and so on, and came up with these reasonable guidelines. And I'm sure a bunch of you are using these numbers today. And if you do put them in production and use them, they'll probably do a decent job for you. You may want to tweak them a little bit though. So my method of removing fragmentation, if you're desperate to pay me to write you some code to do this, right? And I would rather you didn't. I'd rather you downloaded somebody else's code. So what my method is I will figure out which indexes actually have performance issues on them because of fragmentation, either page splits being created or the fragmentation after the page splits have occurred. And I'll have a table called the driver table with a row for every index in there. I'm only going to call that DMV for the indexes in the driver table. If I don't care about the index, there's no point calling the DMV for it. So I limit the amount of work that the DMV does. And then I've got a threshold per index about when to rebuild, when to reorganize, when to do nothing. And that could just be the 5%, 30% thing. Keep a log of what you did so that you can tell whether there's any patterns that have cropped up in what's happening with your indexes. And then another thing that I generally do is I'll keep a counter of how many times in a row when the index maintenance runs, an index has to be rebuilt. And if it's something like 5 times in a row, it gets rebuilt every time, drop the fill factor by 5% down to some minimum level like 50. But as I said, I'd far rather you downloaded somebody else's code and use that. And there are a number of different people that have written free code that do this, but in my mind, the absolute gold standard out there is written by a guy called Ola Hallengren in, I want to say, Denmark. And I hope I didn't offend him by getting that wrong. I want to say Denmark. And it's totally free code. It's won all kinds of awards. It's fabulously cool code. Even if you don't want to use his code and you want to write your own, download his stuff and steal a bunch of it because it's complete freeware. And that's why he writes it. So inside online index operations, a little bit of internals for you. I know this is supposed to be 200 level, but this is really cool to know how this works. So we have an index. We want to rebuild it online. So the first thing that has to happen is a table lock has to get held, a shared table lock. Right? And while the shared table lock is being held, then it builds an empty index, and it recompiles query plans touching the index so that any updates to the old index also update the new index. And also, under the covers, it creates a point-in-time scan called a version scan of the old index. It doesn't go and turn on snapshot isolation. It actually uses a different version store just for this stuff. And then it drops the share lock. So that share lock is a point where there could be contention. And for the long time that the new index is being populated, it's holding what's called an intent share lock, which is a very, very light table lock, which shouldn't cause you problems. When the scan finishes and the new index is populated, it needs to drop the old index. So unfortunately for that, it needs one of these super exclusive schema modification locks, which again could cause blocking. But I say could cause blocking. There's new code in 2014 that allows the online index operation to wait essentially for other things to jump over it for a certain amount of time and then either kill itself or kill the things that are blocking it. So you do have a little bit of control over that. While the schema mod lock is being held, it finishes off with the old version scan. It puts the new index into the old index's place, gets rid of the old index. All the query plans for that table are recompiled, and then the schema modification lock is dropped. So that's in a nutshell how an online index operation works and the 2 points where there is locking that could occur. So very quickly, I'll finish off my demo and get rid of the fragmentation that we caused earlier on. So this is the fragmentation that we have here. So I'm going to get rid of the fragmentation in the clustered index. And I'm going to do that using an online index rebuild. Now, if you're running this code on 2008, oops, I need to be in the right database, of course. If you're running this code on 2008 or 2008 R2, this will fail. And it will say, I can't do the online index rebuild because you've got a lob column in your table. If we scroll back over here, what we'll see is in my table, I snuck in a 1 byte varchar max column. And until 2012, that will prevent online index operations on the clustered index. But I'm on 2014, so it worked. So our fragmentation went from 99% down to, and I'll just rerun that code again, 0.15%. Cool. And we set our fill factor to 70. Now what about the non-clustered index? Okay, so on 2008 R2, you have to do the offline rebuild. On the non-clustered index, let's reorganize it. And our fragmentation drops from 29.58 to 2%. Okay. But with the reorganize, you can't set the fill factor, unfortunately. That's my fault. I forgot about that. Sorry. You have to do an index rebuild or go into the object properties and change the index properties and set the fill factor. So let's just do an index rebuild here. So we'll do an online index rebuild. Oops. We'll do an online index rebuild and see if that changed things. 2% there, 98.97. So here we got to set our fill factor, and it managed to drop the fragmentation a little tiny bit. Okay. So a couple of things there just to demonstrate. I told you it's hard to do a really cool demo around fragmentation. The limitation around lob columns up until 2012, and the fact that you can't set a fill factor using a reorganize. You have to do a rebuild or use Management Studio to do it. So just 2 more slides and we are done. Are your indexes being used? You might have a whole bunch of non-clustered indexes that aren't being used at all. However, if they're not being used, they're still being updated and inserted into when you update and insert records in your table. Could be causing lots of page splits. And if that index isn't being used at all, that's a double waste, okay? Because you're taking a performance hit and you're not even making use of the non-clustered index. And probably if that index is being fragmented, your index maintenance is then defragging it, which is an even bigger performance hit. Okay? So use the DMV index usage stats to tell whether your indexes are being used or not. Google or Bing for that, and you'll come up with a bunch of people, including me and Kimberly, that have written blog posts about how to use that DMV correctly to make sure that you're deciding to drop indexes correctly if they're not being used. So to summarize, fragmentation is expensive when it happens because of these things called page splits. And many people say, as I mentioned, don't bother about fragmentation with SSDs. Just maybe add more buffer pool memory or add some fast drives. Wrong. These things do not stop the extra log records being generated when a page split happens. Also, it can still waste lots of buffer pool memory. It can also waste space on your SSD. Okay? You have to take into account fragmentation, and you have to either remove it or mitigate it using fill factors. So set fill factors, and you now know how to use a fill factor. It's very, very simple. The starting point is generally going to be fill factor of 70, and then tweak as needed, or maybe just walk away, but at least set a fill factor. And if you can, try to set your clustered index keys when you're designing new systems to avoid page splits, because the clustered index is the biggest index, and it's generally going to be the one that's the most expensive to remove fragmentation on. Some pointers to resources. So I've blogged a bit about fragmentation. There's actually a Pluralsight course about index fragmentation, which is a much more expanded version of this session. It's like 3 hours long. And if you've never used Pluralsight, you can email me and try out the Pluralsight stuff. OLA scripts for doing the index maintenance, again, by far the gold standard. There isn't a white paper on this stuff, unfortunately. There's a very old white paper from 2000, which is now 15 years old, and Microsoft has never updated it. The concepts still translate nowadays, but it uses the old DBCC commands. And finally, if you are an insomniac and you want to know more about how online index operations work, there is a white paper. It's very, very interesting. It's very dry and very technical. But if you want to go a little bit deeper, you can learn about how the online index operations work in a bit more depth. And with that, I have finally finished speaking. Only 10 minutes over. I'm sorry, Warwick, for running over your hour. But now, if we have anybody that wants to ask questions, I will hang around for as long as Warwick wants to carry on asking me questions.
All right, thanks, Paul. No problems at all with running a little over time. We do have some questions from throughout the session.
I can do some more slides. No, I'm just kidding.
Okay, so we'll go back to one from earlier on. How can we reduce the fragmentation level if we're using unique identifier columns?
So if you have to use GUIDs, then the thing you can do is you can go and use, if you can, use sequential GUIDs rather than random GUIDs. Sequential GUIDs, it's the same thing. It gives you a GUID, but they're just not completely and utterly random. I mean, GUIDs that are generated by SQL Server are pseudo-random anyway. Sequential GUIDs are a lot less pseudo-random than GUIDs. So if you can, try to do that. What can be even better is if you're able to change your keys, change from, for instance, the GUID being your cluster key to maybe some kind of another surrogate key, because a GUID is a surrogate key, another kind of surrogate key, which is something like an int or a big int identifier column. And if you have to still have your GUID, make that a non-clustered index, maybe even a non-clustered primary key, and have your clustered index key be an int or a big int identity column. That's a topic that we could go on for hours about, is choosing a good cluster key. But if you can, when you're designing systems, bear in mind the fact that random keys cause fragmentation, and try not to do it. So that's basically your options for if you already have GUIDs. Switch over to a sequential GUID, or try to change your cluster key, which is very, very much easier said than done.
Okay, so the next one is there any advantage in having a data file initially sized set high enough to always have enough free space in the data file?
Oh, okay, so not to do with fragmentation. So I think this is getting towards file system fragmentation rather than index fragmentation within the file. And the answer depends. If you have a bunch of data files that are sharing some volume or LUN, or whatever you want to call it, and you have set them to be just big enough, and all of them keep growing, then you could have fragmentation at the file system level, which in extreme circumstances, very, very large scans might cause you a very low single-digit performance hit. It's a general good practice to size your data files to allow SQL Server to have some free space to work with, because it generally needs some free space to work with. So I would say, as a generalization, yes, for a database, data files should have some free space in them. How much free space, that's an entirely different question, because you don't want to have, for instance, a database that has 500 gig of data and you've got a terabyte of data files, and there's no potential for that extra 500 gig of space to be used up at any point in the next year or two. That's just complete overkill. Okay, so you want to be smart about how you do that as well. But in general, yes, I advocate having some free space in the data files. What do you think, Warwick? Do you agree?
I do, Paul,
Yeah.
because it will assist with some of your I/O problems that you may run into depending on how much work is happening on your database.
Yeah, good.
So next question, does database compression help resolve fragmentation?
No. Simple answer. More complicated answer. You might think it does, but it doesn't, because all it's doing is allowing you to have more records on a page. So if you've got more records on a page and you do a random insert into that page, it's still going to do a page split. So all fragmentation does is make your records smaller and allow you to have less pages. So no, there's no gain at all in terms of fragmentation from having compression turned on.
Okay. Can we ignore fragmentation on indexes with lob data?
Well, you can't have an index on lob data. You can have an included column that is the lob data, which is a bad thing to do, and I wouldn't do it, because it creates a copy of the lob data column from your table. Maybe they mean varchar key columns rather than true lob data. No, you can't ignore fragmentation at all, full stop, basically. So no, there's no special case. Okay. In fact, going back to the previous question, I was just thinking about the compression one while I was answering this one. Data compression might actually make things worse, because data compression, all columns become variable length. So if you have an integer column, it becomes variable length, and in one record it might be 1 byte long, in another record it might be 2 bytes long. So you might have an integer where you update what you think is a fixed width 4 byte column to be another value, and it actually makes the column, say, 1 byte longer, because compression will strip off all the unused bytes, and so that record might have to grow in size. So it could actually cause, in some circumstances and some workloads, more potential for page splits rather than less.
Okay. Can the index stats DMF be run on a snapshot and get the fragmentation results?
Yes, it can be run on a snapshot, but don't do that, because snapshots have this nasty little issue where the pages that are read for the snapshot in the buffer pool have to be owned by the snapshot database. So you might have a database where you want to run the DMV on, say, a 10 gig index, and the entire 10 gig index is in memory already. If you create a snapshot and then go into the context of the snapshot and run the DMV on that same 10 gig index, it's going to reread the whole 10 gig index into memory again and have all those pages in the buffer pool be owned by the snapshot database. Okay? Snapshot databases are very, very memory inefficient. So I would never do that. I would always run the DMV. If you have to, just run it on the regular database.
Okay, so the next question, can you check fragmentation against an always-on availability group replica?
Yes, because the replica is an exact structural byte-for-byte copy of the primary replica, and so the fragmentation is going to be exactly the same from one database to another. And a similar question gets asked about can I restore a copy of the database and run the DMVs over there? Yes, because the restored copy is exactly what you backed up in all of the fragmentation within the data files.
Okay, the sequential grid will not be sequential if the machine restarts, and also if the sequential grid generated on multiple machines, then it will not be sequential. So how can we handle the fragmentation in this scenario?
So if you are let's take the first one. The first one, if your machine restarts, then sure, it's going to jump to a different point in the universe of GUIDs and do that. However, sequential GUIDs do that anyway. I can't remember, every 10,000 or so that it generates, it picks another point in the universe of GUIDs, or the space of GUIDs, I should say, and goes from there. So don't worry about the case of your machine restarting, because how often does your machine restart? Very rarely. So you might have, you'll just have a different range of GUIDs being generated with potentially one random insert. I wouldn't worry about that. If you have GUIDs being generated on multiple machines and then being sent to or coalesced into one database somewhere, then essentially what you're doing is you're using random GUIDs. So you would cope with that exactly the same way as you would if you were, for instance, generating GUIDs on that server using NewID, which is you'd have to use fill factors. There's no other way around it. Or don't use GUIDs. So I'm just thinking of the case, for instance, where maybe you're doing peer-to-peer replication and you've got multiple databases that you're writing to, which then get replicated to another system. Instead of using a GUID, you might consider using some kind of multi-part key with an identifier of what the server was that generated the value. And this is a classic way of doing peer-to-peer replication. An identifier that generates that indicates the server, and then some kind of like big identifier that is generated on that server. And by using the two-part key, you guarantee that there can never be a clash, because each server is generating its own bigints, but the leading cluster key value is the identifier, whether that's numeric or character-based, of which server generated the key value. So that's what I would do instead there, just as an idea.
Very good. Okay, so does encryption cause index fragmentation?
No, entirely orthogonal. Well, okay, hold on a sec. I answered too quickly. I was thinking of transparent data encryption, which just happens at the buffer pool level. That's entirely orthogonal. Column level encryption, now I'm not a security person, but if it is possible that you could take a column, encrypt it in some way inside SQL Server, and then store that same column value back, if you could take a column value, let's say you've got a character column, encrypt it, and then store the encrypted value back in the same column, and the encrypted value is longer than the unencrypted value, then you've essentially updated the record to be longer than it was. I don't know whether that's an actual thing that can happen inside SQL Server or not, because I'm not a security guy, and I don't deal with encryption. Do you know? Do you happen to know, Warwick?
No, not off the top of my head, because I don't, like you, I don't do a lot of work with the encryption.
Yeah. So if the scenario that I said is possible, then yes, it could. If that scenario is not possible, then no, it won't.
Okay, if a reorg is stopped in the middle of the process, does SQL keep any previous reorganization?
Yes, so one of the entire reasons I wrote the reorg process was so you can interrupt it. It has two phases. The first phase is it zips through all the pages, essentially compacting them, making the records all compacted onto a smaller number of pages. And then it goes to all the pages that are allocated to the index and it sorts them into the right order. So they're in the same logical and physical order. So if you interrupt it at any point, the most that it's ever going to roll back is one page's worth of moving records around. So essentially it will keep all of the reorging that it's already done. It doesn't remember where it got to, though. There's no record of that at all. And the fact that you can interrupt a reorg is what allows you to perform index maintenance on large indexes if you're using a database mirror or an availability group, because both of those features require the full recovery model. And doing an index rebuild of a large index and generating all that transaction log and then having to have it sent across the wire to your mirror or your AG may be prohibitively expensive. So what you can do instead is a thing I call staggered index maintenance, and I mention it on a slide. Where did I mention it? I mentioned it on a slide back here, where I say synchronous mirroring or AGs may force reorganize to be used. And that's because what you could do if you have your large index is you could, 2 o'clock in the morning, kick off an index reorganize, let it run for an hour, kill it, and then do the same thing every day for 7, 10, 14 days. And each time you're just reorganizing and taking and fixing the fragmentation that exists rather than doing a brute force rebuild of the entire index. So it's going to generate, depending on how much fragmentation there is, a lot less transaction log while it's running. So by doing a set of staggered index reorganizes, you can remove the fragmentation in a large index when you're using a synchronous mirror or an availability group, whereas you can't with an index rebuild because of the log that gets generated. I can't remember what the original question was, but hopefully I answered it. I kind of went off on a tangent there.
That's okay. So the next question is it recommended to do an update stats after an index reorg?
So statistics are not my strong point. That's one of Kimberly's strong points. And what you have to remember is that an index reorganize doesn't touch index statistics at all because it doesn't see the whole index. An index rebuild will generate index column statistics for that index, regenerate them with the equivalent of a full scan. So you need to be careful how you do your index statistics, your statistics maintenance. You don't want to go and rebuild your index column statistics after doing an index rebuild, because at the very least that's a waste of time. And if you do a sampled index a sampled stats update, you're actually going to be getting worse statistics. So depending on what you're doing, if you're doing a reorg, then you should be doing stats maintenance as well. If you're doing a rebuild, you don't need to do index stats maintenance, but you may have to do column statistics maintenance if there's no index statistics on any of those columns. Hopefully that makes sense.
Okay. So when undertaking a rebuild or a reorg, we're unable to be, we don't get given how much of the rebuild or reorganize has completed. How do we find out how much percentage rebuild or reorganize operation has completed?
So for a reorganize, it does do progress reporting. You go to sys.dm exec requests and you look in the % complete column and it gives you full progress reporting. Okay. For an index rebuild, you can't get that. There's two ways to do it for an index rebuild. If you're doing online index rebuild, there's a profiler event called Progress Report Online Index. And if you just happen to include the big int data 1 column, that is how many rows through the version scan the online index operation is. So if you know how many rows there are in your index, you can figure out what percentage of the way through it is. Another thing you could do is, if you know how many pages there are in your index, you could look in sys.dm exec requests and see how many page reads the query has done so far. and you could figure out a percentage from that. But if you're doing a reorganize, it tells you nicely in percent complete. And that's basically because under the covers, it's really a DBCC command, and the DBCC commands are what use the progress reporting framework in DMExec requests.
Okay. Now, I'm pretty sure we can't do this, but why can't MS SQL do a partial rebuild / reorg of what has changed only? So you could do small rebuilds and rebuilds in chunks.
How would it track what's changed? That's the thing. It wouldn't be able to track. You'd have to have basically an extra column in every record, or maybe a column in, or sorry, something in the page header that says it's changed. Now, well, you could. The best way to do it. What you're essentially, there's two things you're asking for is some kind of automated index fragmentation removal and a smart way of doing fragmentation removal. And the smart way of doing it is alter index reorganize, because that is just taking account of what's fragmented. Remember, rebuilds a brand new index all the time. A reorganize only gets rid of the fragmentation that exists. So it's analyzing the fragmentation as it goes along and then removing just the fragmentation that exists. So if I actually step back, reorganize does exactly what you want. Okay. Hopefully that answers that question.
Yeah, it's just the rebuild. I'm keeping track to be able to do a partial rebuild.
You can't. There's no way to do a partial rebuild because of the way the rebuild process works. So I talked about how the online index rebuild works. The offline index rebuild, basically every thread in the parallel rebuild is given, say you've got 4 threads, is given 1/4 of the index. Go and build 1/4 of the index, and then it brings those quarters of the indexes together and stitches a B tree over the top. So there's no way with the current code to do that. And even if there was a way to do it, even if there was a way for a rebuild to know what had changed, how would it put the changed rebuilt portion of the index into the existing index? That wouldn't be possible. So that's why you either got online index or offline index rebuild. There's no way to do a partial rebuild in any kind of worthwhile engineering complexity. Basically, the complexity of the engineering makes it so that it's not even worth doing. Okay.
Okay. So if index fragmentation is over 80%, but pages are between 1,000 to 5,000, we should not worry about rebuilding or reorganizing.
In general. I'm not going to say always. You might have a case where you've got a 1,000 page index that is 80% fragmented, and there is a notable performance increase from removing that fragmentation. In general, I wouldn't worry about it, but you might want to check. Okay.
What would be the best method to eliminate fragmentation on a table that stores session information that has inserts and deletes up to 50 to 1 million rows per day with no maintenance window?
If you don't have any maintenance window, so if it's a 24/7 system and you can't have any blocking, you've got no choice but to use an alter index reorganize, because both kinds of rebuild are going to take at some point a schema modification lock, which is going to block all reads and writes to the table. So you're going to have to use an alter index reorganize.
Okay. Is there any gain in using sequence objects to assign keys?
Anytime you can have an ever-increasing key value for new records, you are avoiding the potential of a page split. So yes would be the answer there. If I'm understanding the question, then yes. Anytime you basically want to have a key value that's ever increasing, because that by definition avoids the possibility of a random insert. But yes. That's only going to be for your clustered index, though. Remember, your non-clustered indexes, they're not all going to be on the same key value. Well, you could, but they'd be pretty much useless. So now, saying that though, you might have 1 or 2 non-clustered indexes that have the same key value as the clustered index, but they're an awful lot smaller, and they're supporting specific queries as covering indexes. But in general, you're not going to have all your non-clustered indexes be the same as your clustered index.
Okay. Now, I'm pretty sure this is going to be a big depends, and we're not going to be able to answer this one, but how much space is required to rebuild indexes on a 4 terabyte database? And the reason why I said it depends is
how big your index is.
How many indexes do we have?
Well, look at it this way. So let me take a stab at this. You're not going to do parallel index maintenance. Do one at a time. Don't do multiple ones at a time, because you're going to be generating tons of transaction log, tons of page reads, and so on. Do one index at a time. So then the answer to the question is, how big is the biggest index in your database? So out of that 4 terabytes, if your biggest index is 100 gigabytes, then the worst it's going to take is 120 gigabytes in that database. And that's for an offline rebuild that has to resort it. So it's 1 times for the new index and 0.2 times for the sort requirement. So there is an answer.
Okay. How reliable of stats in DMDB index usage stats? Can we use it to delete unused indexes?
You have to be very careful. So 2 parts to the answer. Let me just take a quick drink of water. The statistics from 2012 onwards are zeroed out if you do an online index operation on the index, which is really crap. But that's just the way it is, and they're not going to fix that. So you have to be careful of that, first of all. So the second thing is the statistics, apart from that, are 100% accurate. Now, you're looking for indexes that over your business lifecycle have only ever been updated, is what the DMV calls it. In other words, it was changed because somebody did something to the table, right? And the index wasn't actually used for seeks or scans. However, you cannot use that as a determination of whether to drop the index, because you might have an index that is never ever used, and it is enforcing a uniqueness constraint. The very fact that that index is there and is enforcing a column or combination of columns to be unique can allow the query processor to infer things and to generate a more optimal query plan. And if you remove that index, thus removing the constraint, then the query processor can't generate such a good query plan. So the answer is, if an index has never been used, and you know that it hasn't been online index operated on over your entire business life cycle, and it's not enforcing a constraint, then you can drop it.
Okay. We have fragmentation reported for allocation unit type lob data. Does this need to be defragmented?
Okay. So this is one thing that when people write their own index fragmentation code, trips people up, because if you're writing your own code to look at the output from the DMV, you need to look at, let me just go back here. Let's do this one. You need to filter on alloc unit type desk, okay, being in-row data, because that's the only one that a rebuild is going to be able to do anything about. So if it's row overflow data or lob data, you're going to ignore it, because an index rebuild and an index reorganize, well, an index rebuild isn't going to touch it. And the mistake that people make is they don't filter on in-row data, and so they have some lob data which is fragmented, and they keep picking up and rebuilding the index over and over and over every night, because their code trips over the row of output for the lob data allocation unit. Now, saying that, if you have lob data allocation unit fragmentation, a rebuild won't help you at all, because it never touches the off-row data. You then would have to use an index reorganize and allow it to do the lob compaction to try to get rid of that. That's the only way to get rid of it. If you don't want to do it reorganize, the only other option you've got is to create a new table and export the data into a new table.
Okay, so our second last question. Would you be able to use a rebuild on a 24/7 system if you also use caching third-party software?
I don't understand the last part of what you said. If you used what? Third-party software?
caching third-party software.
Oh, caching, sorry. Many countries separated by a common language or different pronunciations. If you use caching software, how would the caching software, well, okay, so I think I know what the person's getting at. If you've got a 24/7 system and you want to do a rebuild, which is going to cause blocking, but you've got some kind of mid-tier cache that's able to satisfy all the queries that happen while the blocking is happening, then yes, you'd be able to do it. Now, the mid-tier cache isn't going to allow you to cache updates, or it shouldn't, so you're going to be stuck there. But if the mid-tier cache can satisfy all of the read requests while the rebuild is happening and causing the blocking, then yes, that would work. But why wouldn't you just use a reorganize? That's my return question to the person to think about.
Okay, and the response was, I will.
Oh, there we go. Okay.
And our last question for this afternoon, is there a way of fixing heap fragmentation on a table?
Yeah, so heap fragmentation is where you've got what are called forwarded pointers. So we haven't talked about those yet because it's not an index, and we're talking about index fragmentation, where in a heap, if there's not enough space for a record to expand, then the record moves to a new page, and there's a little forwarding pointer left in its place. And this is what's called heap fragmentation. And you'll read all kinds of information online saying, if you want to get rid of this heap fragmentation, build a clustered index and then drop the clustered index again to rebuild the heap. It's a horrible thing to do, because when you rebuild when you create the clustered index, it changes all of the linkages from your non-clustered indexes back to the base table, which is a heap or clustered index. Basically, all the non-clustered indexes get rebuilt automatically, and you can't stop it. When you then drop the clustered indexes again, you've changed the linkage again. All the non-clustered indexes get rebuilt again. So they get rebuilt twice, which is horrible. What you should really do if you're suffering from heap fragmentation is build a clustered index and stop. Okay? So now you don't have heap fragmentation. Now you've got a clustered index, which doesn't have heap fragmentation. But then what clustered index key do you choose? And that's a question we could talk about for hours. Now, if you absolutely want to keep your heap, then what you can do is do an alter table rebuild on your table. Alter table rebuild was added in 2008 as a way of being able to turn on data compression for a heap. But if you don't specify data compression, it will build you a new heap. Now that means that all the heap data page locations change, which means all your non-clustered index linkages are broken, so your non-clustered indexes get rebuilt, but only once. So if you have to keep the heap, alter table rebuild. If you don't have to keep the heap, create a clustered index.
Okay, well, thank you, Paul. Thank you, everybody, for hanging around. I think Paul did a fantastic job with Q&A, and thank you for your time. Thank you for
very welcome.
Everybody attending. Everybody have a safe and Merry Christmas, and I look forward to seeing you all next month for Alan's session on the top 10 do's and don'ts with clustering. So on that note, I wish you goodbye. Thank you all.
Goodbye, everybody.